Okay, so there will not be any poll questions today, but I'm gonna give full credit for everyone's joining and everything like that. And, you know, full credit, period. Where can we find the actual homework assignment? I am going to post that in just a little bit. I have two computers that I work on, and the assignment is on my laptop, which I'm on my desktop now. So it'll be posted, within 10 minutes after class today. So I apologize for that. I presume everyone took a look at my message the other. Nope. Yeah. About quizzes. I don't know why. Well, no, I do know why. It's force of habit. Every semester I give quizzes. This semester I'm not doing quizzes in this class. And so I said, "Oh yeah, you have a quiz coming on Thursday." There will not be a quiz posted today because we don't have quizzes. They're not a part of the grade. Now, with that said, if you're thinking, I want I want practice questions. I want to simulate what it's like. Well, I've got the practice exam. I'm going to continue to populate that with more and more questions. Um, and your practice exam you could kind of look at that as a good repository of test type of questions that I want you to be able to answer. Right now, there's only 10 questions in there, but it's the style of questions that I want you guys to have. Um, and that I think will be helpful for you on your exam. Your homework assignment, like I said, will be posted a little bit after this class. I apologize. I've got the assignment up, but I don't have the actual document, so I apologize for that. All right. So, what we've been talking about over the course of this semester is we've been looking into amino acid structures, and we just added an element last time, and that was the peptide bond. Now, that allows us to draw a larger molecule and to visualize a larger molecule. Now, if you look on the far left-hand side of this slide right here, you see that same peptide bond visual that we looked at last class period. Well, think about this screen as kind of a progression. So this is amino acid number one bound to amino acid number two in a peptide bond. That gives way to a larger molecule being something like this right here, where we're looking at a large, higher ordered structure, and that gives rise to this thing right here. So this, on the far right-hand side of this slide, is a protein. So this is something, maybe it's like 500 amino acids come together to make that. Now, amino acids, understanding those individual molecules is essential for understanding how a protein functions and what a protein looks like. This right here is a folded protein. And I could just as easily put the parentheses around protein as well, but this is that protein in its 3D shape. And let me ask you guys and add to the chat, what is this thing made up of? Okay, Favor, you jumped ahead a little bit. I was looking for amino acids. You're right. You added beta and alpha helices, beta sheets and alpha helices. You're right. We're going to get into that, but what I was looking for was amino acids. This molecule is just a bunch of amino acids. This could be somewhere in the order of like 550 amino acids. Now, that gives us, and if you've ever taken a biology class, whether it's like a foundational biology class or a cell biology class, you've maybe learned about proteins and you've maybe learned a little bit about their organization and their structure. We have different levels of protein structure. What we've kind of talked about is the primary structure, and we're going to more or less live in the primary structure today. On Tuesday, we're going to get more into secondary, tertiary, or secondary structure as well. And then next Thursday and Friday, we're going to talk about tertiary and quaternary structure. I feel like this is a good place to start because this gives us a way of thinking about individual molecules and kind of the chemistry that those individual molecules can participate in. And then you build onto that. And whenever you get, so let's say that in the primary structure, we see an arginine. An arginine is a positively charged amino acid. That positively charged amino acid can gladly interact with a negative, or let me just rewrite that. It can interact with an anion. Okay. Now, this arginine is a part of this polymer. When we get all the way down here to the quaternary structure, this highest order, this three-dimensional structure of a protein, let me just ask the same question. Can part of this right here, part of this quaternary structure, can that interact with an anion? A Y or an N to the chat. Let me rephrase that. Can it still interact with an anion, a negatively charged ion? And let me rephrase it. Does it still have that arginine? Yeah, absolutely. Since it still has that arginine as a part of one of its building blocks, it can still interact with an anion. So it's really important that as we go through these different levels, that you understand the chemical properties at the primary structure, in many cases, are retained all the way through the highest order structure. So when we look at something like this kind of progression, the chemistry that this structure is able to do is going to be preserved for the most part in the chemistry that this thing is going to do. Okay, now we'll revisit this, but all of these different structures have different stabilizing forces. The covalent bond stabilizes the primary structure of a protein because the peptide bond is an example of a covalent bond, and that's what connects two amino acids to one another. Now, your primary structure is read from the N to C termini. It's stabilized by a covalent bond, and we saw this the other day where a one-letter and three-letter codes are used to label that sequence from the N termini to the C termini. The primary structure the amino acid sequence, up to 50 amino acids, it's referred to as a peptide. Anything more than that, it's known as a protein. Now, this is one of the things that we kind of talked about the other day, and it's important because we're going to bring it back. And we're going to tackle this kind of drawing of a molecule. But one of the things that I want to add, or two of the things that I want to add are I want to calculate the PI, and I want to show you a titration curve of a peptide. Now, before we do that, what I want to do is I want to give you three different amino acids. L, and whenever you're ready, add to the chat what the single letter code L, what's the full name for that amino acid. ASP, when you're ready, add the full name for ASP. And then last but not least, add the single letter code for the amino acid histidine. Great. Awesome. Great job. So L is for leucine, or the three-letter code is LEU. ASP is the three-letter code for the amino acid aspartic acid, also known by the single letter code of D. Histidine, well, that is H or HIS for the single and three-letter codes respectively. Now, when it comes to these different amino acids, one of the things that I want to bring back is that L is a non-polar amino acid. Aspartic acid is polar negative, and histidine is polar positive. What I want to do with all of these different amino acids is I want to draw them at a pH of 1. Then I want to draw a titration curve for each one of these amino acids. So I'm going to toggle back and forth between a couple of slides because I've got the I've got the pKa's that I'm going to need. And then I also want to look at these structures. Okay. So what I'm going to do first, however, is I'm going to draw the backbone for all of these. N, C, C. N, C, C. N, C, C. I'm drawing these at a pH of 1. So the N termini is going to be H3 plus. I'm not drawing these as a tripeptide, but instead drawing them as individual amino acids. H3 plus. H3 plus. For each of the alpha carbons, I'm going to put a H. And then for the C termini, double bonded O and OH. Double bonded O and OH. Double bonded O and OH. So that's my backbone whenever my pH is 1. So as protonated as it can possibly be, that's what I've got. Now, if I were looking at and calculating the charge of this molecule, they would all be +1. But I know that I still have to draw my R group. I'm going to change colors and I'm going to switch over to green. Sounds good. So now what I want to do is I want to look at leucine. Leucine is captured right here. And I'm going to circle the R group for leucine. That is a non-ionizable R group. So regardless of the pH, that non-ionizable R group is going to look the same at a pH of 1 or at a pH of 14. I'll go back a couple of slides. Show you this. So we've got CH2, then CH3. Okay, let's make sure that I did that right. I've got this carbon right here, which I don't know if anyone ever has been to like GNC or Total Nutrition or something like that, one of those nutritional or dietary supplement places. Um, if you have, they've possibly mentioned as a if anyone's ever used like a pre-workout supplement, pre-workout supplements, they're all pretty much the exact same. They've got carnitine, which is an amino acid. They've got some B vitamins. They all have caffeine. And then one of the other things that they have are known as beta branched amino acids. Now, I bring that up because that's something that people like to throw the term out there and you just, as a consumer, I've been in this situation where it's like, oh, okay, cool. Yeah, it's got that. Awesome. You got big muscles, so that's what I'm here for. Well, we know that this carbon right here is our alpha carbon. That is, by comparison or by proxy, that is our beta carbon. And so when you see a beta branched or hear about a beta branched amino acid, that means that there's a methyl group coming off of that beta carbon. So an example of a beta branched amino acid would be something like isoleucine here. Okay, but that's not why we're here. I just wanted to bring that up so anyone could hear that if they were interested in it. Now I've got my leucine drawn. Okay, next up is going to be aspartate, and aspartate is going to have CH2 and then a carboxyl group. Okay, I'll go back to look at. Did I not? No, I didn't include that one in this one. Okay, so that's what that looks like. Then histidine. Oh, dang it, Joel, why'd you do this? Why'd you do this, Joel? I'll copy and paste this. Just a second. I apologize, everyone. Boop, boop, boop. Okay, here we go. Aspartic acid And then histidine. There we go. Got them copied. Now I can slide through. You can see it. Okay, so there's aspartic acid, which is what I drew. And then histidine, we've immediately got this ring structure coming off of histidine. So I'm going to go back and we're going to draw histidine. Okay. Now, with histidine, what we need to do is we need to account for, well, we've got two nitrogens there. And we're going to have a nitrogen that is positively charged and then one that's not positively charged. So there we go. There we go. So there's our histidine. And this is what it looks like at a pH of 1. Now, the next thing that I want to do is account for my pKa's. So if we look at our charts of pKa's, we'll see that the pKa's for the N termini and the C termini, N termini is almost always about 9. Sometimes it's higher, sometimes it's lower. And then the C termini is typically around 1, or 2, sorry. So aspartate, I'm going to come up with the same table, N and C, about 9 and about 2. Histidine, N termini is about 9 and C termini is about 2. But we also need to know our R group. Now, aspartic acid, also known as aspartate, has a acidic group. So could everyone add roughly what they think the pKa of this group is going to be? And I don't need you to know it specifically. 3, I like it. We're going to use nice round numbers. 3 or 4, great job. So we've got those 3 pKa values. Now, I like to just throw some rough ballpark numbers at you because that's where I want you to really appreciate you don't have to memorize those numbers. I do not want you to memorize those numbers. I will always give you those numbers on your exams uh, or your homework. And if I don't give it to you on your homework, I'll ask you to look it up and say, hey, or use the ones from our slide decks because I do have them on here. I just wanted to show it this way. Now, our histidine. Histidine is kind of unique. It has a pKa, its R group has a pKa of approximately 6. Okay. Now, after that, what I want to do is I want to show you guys a titration curve for leucine. Now, leucine will have 2 pKa values. Now, my y-axis of my titration curve is going to be my pH, and my x-axis is going to be, I'm going to put bracket OH equivalents. And I'm going to put that there because, and it might be a little bit confusing, but I want you to think about whenever our pH is equal to our pKa, what do we have? We have a mixture of a particular molecule, a 50-50 mixture. So what I'm going to do on my y-axis is I'm just going to put 2 points, 2 and 9. The next thing that I'm going to do is I'm going to label my x-axis, and I'm going to label it 0.5, 1.0, 1.5, and 2.0. Now, what I'm going to do with this is I'm going to find the coordinates where it's 2 and 0.5. And I'm going to draw my titration curve that looks a little bit, oh, that wasn't good. I'm going to redraw that one. I'm going to start at my origin and just kind of go up. Is that similar to a portion of a titration curve that you've previously seen? Add a Y or an N to the chat. Yeah, good. Okay. Now I'm going to do the same thing at 1.5. That is going to coordinate with 9. Now, the reason that's going to coordinate with 9 is because that is, sorry, the second point, or the second point where a pH is equal to a pKa. And that is the second point where I will have a 50-50 mixture of one form of my molecule. Does everyone follow that? Add a 1 if you follow, a 2 if you don't follow what I'm saying. Okay. So I have 2 points in here on this titration curve, or when you do a titration, where you'll have a 50-50 mixture of, and let's look at leucine, where you have this form of the molecule that's shown here, and another point where 50% of it looks like this, where 50% of it will be deprotonated on the C termini, and 50% of it will be protonated on the C termini. Then, if you look at the other part of our titration curve, there will be a point, and that point is at a pH of 9, where 50% of the molecule looks like this, and the other 50% looks like that. So those are our 2 points that we need to be interested in. Now, along the way, if I'm going to get the other bookend of my titration curve, it's going to look like this. Would everyone agree with those 2 curves that I've drawn? At an A, if, okay, that resembles what I've seen before, or a B, if that looks nothing like what I've ever seen before. Okay. Now, to complete this titration curve, and if anyone has never seen a titration curve that looks like this, maybe I'm hopeful that this will kind of populate and fill in some of the gaps, or fill in any sort of disconnect. So we're going from here. Now we've got this very vertical portion. Looks like that. Okay, so that's kind of what we're looking at as a titration curve for a diprotic acid. And just so I can kind of validate myself, I'm going to do a Google search for titration curve diprotic acid. Okay, yeah, I feel good about that. I'm going to go ahead and share this, not to be like, see, but just so you can, yeah, so you can see what I'm going for. There we go. So essentially, my curves that I've drawn are a little bit more dramatic than this, but they're fairly similar. Now, when you look at the titration curve that I drew just a moment ago, I'm going to label a couple of points. Sorry. Okay. What I want you to do is now, let's say A, B, C. Tell me in the chat which letter corresponds to an equivalence point. B. Perfect. Great. Now, what's kind of tricky about biochemistry is that equivalence point right there. That means something. And that tricky point is significant because it corresponds to what is known as the PI. The PI is also known as the isoelectric point. The isoelectric point is the point where 100% of the molecules in a solution, so if you have a solution with 100 million copies of this molecule, every single one of them has a net charge of 0. Now, when you think about that, does that mean, add a Y or an N to the chat, does that mean that none of the molecule has a charge at all? You're absolutely right. That just means the net charge is 0. That means there could be a positively charged region and a negatively charged region. So if I point to this, and I point to this, can you tell me what is the pH for point A on this titration curve? And then tell me what is the pH for point B on this titration curve? Looking at that y-axis there. Okay, 2 and 9, perfect. Okay, could anyone tell me what the isoelectric point is? And take a pause and think about this for a little bit. Try to visualize where it is approximately. And if this would help at all, I'm going to draw a line. Okay, I've got to vote for 7. Draw a line from A to B. I'm getting lots of 7s. And for all the people who wrote 7, oh, one person got it. 2 people got it. Would you agree with me that this point where I'm putting an X is halfway between here and here? Yeah. So the halfway point between those two numbers is the average of them. So you add up the 2 and the 9, and you get, well, 2 plus 9 is going to be 11. Divide that by 2 is 5.5. Does that make sense? Add a Y or add a 1 if that makes sense, a 2 if that doesn't make any sense. Okay, I'm seeing lots of ones. Great, 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 great. Happy to see that. Okay, so I'm going to paint with a very broad brush here. If you are shown, let's say this right here, this chart right here. This chart on the right-hand side shows all of our diprotic amino acids. Could you calculate the PI for all of these diprotic amino acids? Add a Y or an N to the chat. Yeah. And I say that with confidence that you could, because all that you do is add them up and divide by 2. So the PI for all diprotic AAs is both pKa's added and divided by 2. Okay, now I'm going to go back here because now we've got aspartic acid and we've got histidine. We've got 3 pKa's. Now, the point here is we have to be able to reconcile the charges. What we are interested in is we are trying to find out at what pH does our molecule have a net charge of 0. That's our goal, that's our objective. That's the definition of PI. And a fair question for that is, oh, why? Why does that matter? Well, that is the pH where the molecule is least soluble. So I'd like you to think about this in the context of Gen Chem 2, and specifically your Gen Chem 2 lab. In the Gen Chem 2 lab, one of the things I remember as an undergraduate, and I know observing this of people doing this in Gen Chem 2 lab, is you do some centrifugation. You separate an insoluble fraction from a soluble fraction. You've got your precipitate and you've got the pellet. You've got your pellet or your precipitate and you've got your solution. Where I'm going with this is if you adjust the solution, or if you have a protein in a solution and you adjust the pH to that protein's pI, so you got protein X in solution, you adjust the pH to be equal to that protein's pI, does that protein go into the pellet or the supernatant? P for pellet, S for supernatant. Pellet. Okay. Now, you might be thinking, well, that doesn't really help us, but it does. Where is the protein? Do you know where it is? Yeah, it's in the pellet. So what can we do with the supernatant? Get rid of it. We don't need it. We don't care to have that anymore because we have precipitated our protein out of that. Okay. Now, what I want to do is I'm going to go to another page so I can have a little bit more space to work with, so I can do the PI calculation titration curve for aspartic acid. So here we go. We'll come back to those other slides. So aspartic acid. Actually, you know what? I'm just going to work with it here. We've got pKa of 9, 2, and 3. Give me a 1 in the chat if you're good with those numbers. Great. I'm going to draw my titration curve. My titration curve, my y-axis, I'm going to put 3 numbers on it. 2, 3, 9. Now, if I were to, I'm going to draw my titration curve. I'm going to put my pKa values on here. And sorry for any less than stellar renderings. What I want to know is if I put an X right here, can you tell me what the predominant form, what will the charge be of the predominant form of my molecule where that X is? And just a little bit of a spoiler, my pH at that X is below 2. 1, you're absolutely right. Where that X is, the molecule is going to have a charge of +1. Now, what if I say Y? Right there. The predominant form of my molecule will have what charge? It's a little bit trickier, but I'll give you a spoiler. It's not +1. It's not 2, it's not 3. You know what I'm going to do? I'm going to draw aspartic acid in different forms. You're absolutely right, it's 0. Okay, so NH3 plus C. We're going to draw all the different forms of aspartic acid. This is our fully protonated form. That is what is going to be most abundant at a pH of below 2. The first group to be deprotonated is going to be the group that has the lowest pKa. I'm going to erase this and give myself a shorter line. The group that has the lowest pKa is this one right here. So that's the first group that's going to be deprotonated. So I've got H3N plus CH, C, O, O minus. CH2. My R group is still protonated. Now, when I draw my third structure, my R group is going to be deprotonated. And that is going to make my molecule look like this. O minus. That C termini is still deprotonated. CH2, C, O minus. And last but not least, I didn't account for all the space that I would need, is H3N, or wait, no, H2N, C, C, O minus, CH2, C. My R group has been deprotonated already. And the last one is that right there. Can you please explain how you got pKa? How I got these pKa's? These were numbers that I decided. I told you these were the numbers. If you're asking, how did you experimentally get the pKa? Well, that is by running the actual experiment to get a pKa. So these numbers correspond to the strength of the acidity. Now, with that in mind, you will be provided with these numbers. Whenever I said, oh, I just made these numbers up, I'm not saying all pKa's are made up and that they're made by me or anything like that. Does that answer your question, person who privately messaged me? Great. Okay. So these four different depictions of aspartic acid, is everyone good with those different depictions? Does everyone follow those? Add a Y to the chat if you follow that. Okay, great. So these are the four depictions of aspartic acid. This, where I'm going to put an A, is fully protonated. This is what's going to be present and most abundant at a pH of below 2. This that I'm going to put an X by is fully deprotonated. Now, each one of these different groups have different pKa values. So we've got a 2 over here, a 3 down here, and a 9. Those numbers are going to change based on what you see on your exam. And again, I will give you those numbers. Now, the first group that's going to be deprotonated is this one right here, the one with the lowest pKa. The next group to be deprotonated is this one right here with the second lowest pKa. And then the last group to be deprotonated is this one right here. Now, with that in mind, what I always like to do whenever I'm drawing a titration curve is I like to look at these molecules and visualize approximately where they are the most common. Now, whenever I point to this specific point where my pH is equal to my pKa, which forms of my molecule are present there? Add it to the chat. I've got 4 different forms. Add to the chat at that pH where I've drawn a green arrow. Tell me which letters are going to be present in that solution when my pH is equal to 2. Seeing everyone put A and then AB. It's A and B because when my pH is equal to my pKa, I've got a 50-50 mixture. So I've got A and B present. When my pH equals pKa, you have a 50-50 mixture. Now, whenever I go over here, and I point to this arrow right here, do I have a 50-50 mixture right there when my pH is equal to 9? Answer Y or N to the chat. Yes, I do. I have a 50-50 mixture. Now tell me, my 50-50 mixture, what does that consist of? Which molecules does that consist of? Yeah. C and D, you're absolutely right. What about right here? When my pH equals 3, what do I have? B and C. Perfect. Now, with all of that in mind, this is a solution, so it's going to change. So we've got different components in this solution. But if I added this molecule right, or if I added aspartic acid to a solution with a pH equal to, well, 7, am I going to have any form A when my pH equals 7? Add a Y or an N to the chat. No, I'm not. Because it's going to get deprotonated, because this molecule can gain or lose protons based on what's in that solution. Now, what I want to do is I want you guys to be able to tell me information about what charge is present, what is the pI of this molecule. We're going to do this, and then we're going to go on because we're going to use this as a building block for doing the same thing but with a peptide. Okay. This molecule A has a net charge of +1. Molecule B has a net charge of 0. Molecule C has a net charge of -1, yep. And then molecule D has a net charge of -2. Can you add a Y or an N to the chat if you follow that and you agree with that? A Y if you follow, an N if, nope, I don't get that. Okay. What I'm looking for is I'm looking at all of the different groups that I have in my molecule, and I'm saying, okay, this ionizable group has a charge of +1. This has a charge of 0. This has a charge of 0. 0 plus 0 plus 1 is +1. I go on to molecule B. +1, -1, those effectively cancel. This third group has a charge of 0, so I'm looking at a charge of 0. -1, +1, plus -1 is 0, -1. Okay, so that molecule has a net charge of -1. And then last but not least, this is nothing plus -1 plus -1, which gets us to -2. Now, that's where all those different charges, those net charges are coming from. What we want to be able to do is we want to say at what pH does 100% of our molecule have that 0 charge? Essentially, at what pH does 100% of our molecule look like this? Not like this, not like this, not like this, but like this right here. At what pH does 100% of our molecule look like that? And the way that we do that, we've got to vote for 6. How did you arrive at 6? I mean, it's a fair guess. 9 plus 3 divided by 2. Okay, I like that. But let's think about this. We've got this right here. That's where our pH is equal to 9. Then this is going to be 3. Okay, but why didn't we include this pKa? 4.67. Interesting. Okay, well, let's think about this for a second. So if we were to draw a dashed line right here for that first pKa, then our molecule on this side, like within this range, our molecule is going to have a +1. Now, the predominant form between a pH of 2 and 3 is going to be 0. 2.5, huh? Okay. And then between a pH of 3 and a pH of 9, we're looking at, well, the molecule having a -1 charge. Any pH above 9, our molecule is going to have a -2 charge, and it's going to look like this. So what we want to do is we want to find out where 100% of our molecule has a charge of 0. That's our pI. The way that we do that, I think the easiest way to do it is to visualize or draw or understand what are the possible charges that your molecule can have. We came up with our 4 different depictions of this molecule having a charge of +1, 0, -1, -2. Whenever our pH is equal to our lowest pKa, which is 2, we have a 50-50 mixture. Tell me the charges of the two molecules that we have a mixture of when our pH equals 2. One and zero, +1 and 0. Perfect. Okay. Now tell me whenever when our pH is equal to our next pKa, which is 3. We have a 50-50 mixture. Tell me the charges of those. 0 and -1. Perfect. What we are going to do to calculate our PI is to take these two pKa's, the 2 and the 3, those pKa's that basically flank or on each side of our 0, add them up. 2 + 3 is going to be 5, and divide by 2. So 5 divided by 2 equals 2.5. Can you add a Y or an N to the chat if that makes sense? Okay. Now, I want to pivot a little bit. So that's our PI. Could you tell me at what pH does 100% of our molecule have a -1 charge? I got to vote for 6. I got to vote for 3. I got to vote for 5. 100% of our molecule has a -1 charge. This right here, not at the PI. The PI is unique, where 100% of your molecule has no charge whatsoever, or no net charge. We've got 3 pKa's. 6. Absolutely right. So now, one thing that I want to do is I want to remove structures from this. And let's just talk about it. Okay, let's say that we have a molecule that could have a charge of +4, +3, +2, +1, 0, -1, -2. These are all the possible charges that this molecule can have. Now I'm going to give you some pKa's. 1.6, 1.9, 2.7, 3.4, 5.2, 6.8. Let me ask you, do those pKa's, when you read them from the left to the right, do they increase or decrease? Add an I for increase, D for decrease. They increase. 1.6 is smaller than 1.9, which is smaller than 2.7. So reading left to right, they are increasing. Why is that? Well, the reason for that is because I'm visualizing this molecule where it's completely protonated. It's going to be completely protonated at the lowest possible pH. I'm going to have pH of 1, and my molecule will have a charge of +4. Okay, now tell me, what is the PI of this molecule? $4.3. Perfect. Did we have to see the molecule? Y or N to the chat? No, not necessary. Did we have to be able to draw and know that, oh, well, that's a methyl group or that's a carboxyl group? No, not at all. What we needed to do was put this number line to get. How did I get 4.3? fantastic question because, well, what is the pI? The pH where my molecule has a net charge of 0. Okay. Now, think about these +3, +2, +1, 0, -1, -2. Those are my net charges. If I want 100% of my molecule to have a charge of 0, then I want my pH to be above 3.4, but below 5.2. So I'm going to take those two pKa's, 3.4 plus 5.2. 3.4 plus 5.2, that gives me 8.6, divide by 2, and I get 4.3, which is above 3.4 and below 5.2. So that is my pI. Now, I'm going to ask a follow-up question. The same approach. What if I wanted 100% to be +3? At what pH is 100% of my molecule going to be +3? 1.75. Because you take the flanking pKa values, you add them up and divide by 2. Okay. So, a couple of things to take away from this. The pI is unique because that's the point where your molecule is least soluble. So that's a physical property. Your molecule is least soluble when it is at its pI. Second thing is, does your molecule have any charges? Yeah, but the positive charges and the negative charges will effectively cancel out. Now, if we look at histidine, and you know what? I'm going to go back to this right here, and I'm going to get the exact pKa's. 9.18. 9.18. That's my N-terminal pKa. Then I'm going to go back here and histidine, 9.18. 6.10 is my R group. 6.10. And then 1.77. We'll work through histidine and come up with, well, the pI and a bunch of other stuff. Tell me right here, when histidine is completely protonated, what is the overall charge of it? Spoiler, it's positive, but you got to tell me the number. +2. I like it. Okay. Now, I'm going to give you a follow-up. A, B, and C. Tell me, when we're titrating histidine, we're adding some base to it, which group A, B, or C is going to be deprotonated first? B. Spot on. Whenever that group gets deprotonated, what's the charge going to be? +1. Okay, so now I've got the first part of my number line. +1. Okay. What's my next group that's going to be deprotonated? A, B, or C? Well, B's out. C. Perfect. Whenever that group gets deprotonated, what is my overall charge? 0. Last group to be deprotonated is A, and that will give my molecule a charge of -1. So when all of the groups on histidine have been deprotonated, it will have a charge of -1. Now, before we go on and start filling in some more information, can histidine ever have a charge of -2? Wire N to the chat. No, can't. Can histidine ever have a charge of +5? Nope. Can it be +2? Yeah. Can it be +3? Nope. So histidine has this range of charges that it can possibly take on, which is true of every molecule. Now, what I'm going to do is I'm going to take those pKa values and I'm going to write them on top of this number line. 1.77, 6.10, 9.18. Did I arrange those numbers in the correct order? Yes or no? Y or N to the chat. Perfect. What's my PI of histidine? $7.64. Great. Okay. Can you give me a Y or N to the chat if you followed all of this for histidine, applying it to histidine? Okay. Now, I'm going to ask you this question. On a scale of 1 to 5, 1 being super easy, 5 being very difficult, um, the addition, adding two numbers, was that difficult? 1 to 5. It's pretty easy. Um, and then when you divided it, when you divided a number by 2, 1 to 5, where was that? Okay. Now, with that said, the math component of this, pretty simple. I'm seeing lots of ones here indicating, yes, I got that. I'm down. Conceptually, this has some layers. So this to me, like PI calculation, is not trivial. It's it's easy when you get all the different parts, but understanding how to put the parts together is the challenge. And based on what I saw with the 7.64 that you folks were putting in, I think that you're getting it. This is tough to wrap your mind around because you're thinking about it as, okay, well, I've got this molecule in this solution that's changing. What is it now? What is it now? What can it be? I have to juggle all of these things. I want you to take a pause now and be like, I'm getting this. Do I have it 100% right now? Maybe not, but I'm getting it. So I want you to recognize that this is not trivial. This is challenging, and you are getting it, and you are getting there. Okay? Now, with that in mind, when we look at these different pKa values, right here, for example, there's a temptation to say, oh, well, I just add up these two. I add up the R group and the N group, and then I divide by 2. No, don't fall into a trap of being like, oh, well, I can kind of skip this number line thing. I just know to get these two numbers. The reason that I suggest that you do not fall into that trap is because if you fall into that trap, you're going to get some answers wrong. Now, can you give me a Y if you would like me to do another amino acid, or a N if you'd like to go on to do a peptide? Okay. It looks like I'm going to do another amino acid, so I will do that. But I did get a private message question of, so is that why you don't add the 1.77 and 9.18? Yes. Yes. That's exactly why. Do not look at the pKa values and be like, oh, okay, yeah, I'll just grab these two. This number line, this will get the question right every single time when that number line is constructed properly. What I'm going to do is let's go ahead and look at, oh, I know. We're going to look at cysteine. Now, cysteine shown right here. This is a sulfur atom. Cysteine with the single letter code of C. Well, it's got the N termini that's ionizable, the C termini that's ionizable, and the R group that's ionizable. Does anyone remember what this functional group, this dash SH, do you remember what that's called? Give you a hint. I hope my microphone picked that up. A thiol. You're absolutely right. That's a thiol functional group. I got a private message. Can you explain how to construct the line more detailed in the new example? I will do my best. Okay, so we've got cysteine, which is a thiol, or it has a thiol functional group. That is an ionizable functional group. Now, if anyone would please take a look at cysteine, I'm going to erase this. Tell me what the charge of cysteine is as it's depicted right here, which is what it looks like at a pH of 1. It's +1. Okay. I'm going to jump ahead. And I'm going to start constructing that line. So on the far left-hand side of my number line, I'm going to pick its most protonated form's charge. The most protonated that cysteine can be is +1. Now, cysteine has, oh, wrong way, 3 pKa values. Oh, it's got 2.05, 8.0, and 10.25. Okay, good to know. But what that means is I've got 3 protons that I can remove. Now, thinking about cysteine, if it's got 3 ionizable groups, I'm going to draw 1, 2, 3 arrows. Does everyone follow that? Add a Y or an N to the chat. 3 ionizable groups, 3 arrows. Now, when I remove a proton from one group, so whenever I lose 1 proton, my overall charge is going to go from +1 to what? Add it to the chat. 0. Okay. So essentially what this means is as I make my environment a little bit more basic from the pH of 1, slightly more basic, that I've got copies of the molecule with a charge of +1 that transition to 0. Okay. Now when I deprotonate my next group, I'm going from 0 to what? -1. Okay. Before I proceed, could everyone give me an X if you follow, or a Z? Oh, no, not a Z. A O, the letter O if, wait a minute, stop the press. Okay. The last charge, so this is the opposite extreme. When my molecule is completely deprotonated, what is the overall charge of my molecule? -2. Perfect. Okay, I got a message that was, how did you get +1 to start? The way that I got +1 was whenever I draw my molecule, or whenever I look at this right here, this form of the molecule is completely protonated. So I add up those charges. My N termini has a charge of +1 right there. The thiol is neutral. And my carboxylic acid, or my carboxyl group, is also neutral. So I looked at those charges and I say +1 plus 0 is still +1, plus 0 is still +1. I hope that clears that up. So that's how I arrived at that +1 charge. Now what I'm going to do is, so this is, and I have no qualms mentioning this again, this is why I always draw my molecules at a pH of 1. As protonated as they can possibly be, that's what this looks like. So now add a 5 to the chat if cysteine could have a +2 charge. Add a 6 if no, it could not have a +2 charge. Perfect. Cysteine is not going to have a +2 charge. It can't. There's nowhere else that it can put a proton. Will we always start at a pH of 1? I would recommend that. All the depictions of the amino acids that I share with you, they will all be drawn at a pH of 1. If you go look on Wikipedia or something like that, it's a little bit dicier. But you'll always see a note like this molecule drawn at pH of 7.4 or something like that. Okay, so I always start at 1 because that helps me put this line together. So now I'm going to go ahead. I've got this number line. Now what I want to do is I want to add my pKa values. What's my lowest pKa value? 2.05. Do I care that it's add a Y or an N to the chat? Do I care that it's for the C termini as opposed to the N termini or the R group or anything like that? I don't. All I care is that is the lowest one. So I'm going to put 2.05, and that is a 2, not a lightning bolt or a Z. 2.05. Then my next pKa, 8.00. Oh, it's for my R group. Does it matter that it's for the R group? Add a Y or an N to the chat. Again, does not matter. I do not care. It is completely irrelevant which group it's coming from. I'm going to write 8.00. Okay. My last pKa is 10.25. It's for the NH3, my amino group. Again, I don't care where it came from, so we just put the lowest to start no matter what. Yep, because I want my lowest or my most positive charge when it's fully protonated to correspond to my lowest pKa. Because I've drawn my molecule, or whenever I draw my molecule at a pH equals, I'll say 0. When my molecule is in a solution with a pH of 0, that's the charge that I want to show there, +1. So now with this, well, what's my PI? 5.025. Yep. My PI is 2.05 plus 8, which is going to be 10.05 divided by 2 equals 5.025 or 5.03. Okay. On a scale of 1 to 5, this represents the pH, not the pKa. The pH, not the pKa. This PI, the PI is the pH where your molecule has no overall charge. I thought we don't add the R group. We do include the R group pKa value whenever it's relevant. Leucine we didn't because leucine's R group doesn't have a pKa value. We don't care, like this 8 being from the R group, we don't care that it's the R group. We are just listing our pKa values in sequence from lowest to highest. PI value of the whole AA at 0. The PI is the pH that makes your molecule have an overall 0 charge. Does that, my most recent questions, did I answer those? So the number we get when we divide is in pH and not pKa. Yes, because the pKa is a chemical property of an R group or of a functional group, whereas a pH is a property of a solution. So the pKa's do not change. Okay. Now I'm going to go ahead and we are going to do a tripeptide. We're going to calculate the charge of a tripeptide. Okay. So let's imagine that we have the tripeptide ARK. Do we need, or so ARK, that's a tripeptide, alanine, arginine, lysine. A peptide bond connects the alanine to the arginine. A peptide bond connects the arginine to a lysine. Now, if we are looking at A, R, and K, I'm going to pull up in another window these pKa values so I can see them and I'm not making them up or not arbitrarily using them. But trust me on these. N, R, and C. Okay, I'm going to fill in this table with my pKa values for my different amino acids. So the N-terminal pKa for alanine is 9.87. Alanine does not have an ionizable R group, so it has no pKa for its R group. 2.35 is the pKa for the C termini of alanine. Arginine, my next amino acid, has an N-terminal pKa of 9.04. Its R group has a pKa of 12.48. Its C termini has a pKa of 2.01. And lysine, or K, has a pKa of 8.95 for its N termini. Its R group has a pKa of 10.53. And its C termini has a pKa of 2.18. Okay. So now I want to know, add a Y or an N to the chat, do we need the 9.87 for this analysis? Yeah. Now, do we need the C terminal pKa for alanine, or is it involved in a peptide bond and therefore we don't need it? Correct. We do not need, because it's a part of a peptide bond. And I'm going to scribble this out for dramatic flair. What is the other part of the peptide bond that connects alanine to arginine? You can add the number if you want. 9.04. We don't need that either. Same thing goes for the C terminal of arginine, the 2.01. We do not need that. And then last but not least, the other part of our peptide bond connecting arginine and lysine is the 8.95. Okay. So can you add a Y or an N if you follow that so far? Great. I omitted pKa values that are not necessary because these different functional groups are a part of a peptide bond. The C termini of alanine, I omitted that because that is not an ionizable group. You always include R groups. That is absolutely correct. You do not always include N termini and C termini. If they're involved in a peptide bond, if they are free, however, like the 9.87, the N termini of alanine or the C termini of lysine, those are both ionizable still because they're not involved in peptide bonds. Now, what I like to do is I'm going to redraw my molecule, but I'm not going to draw the molecule. Instead, I'm going to draw kind of a model of it. I want you to tell me at a pH of 1, Will the N-termini of alanine be protonated? Y or N to the chat? Yes, absolutely. Now, what about the R group for alanine? Why do them being a part of a peptide? The R group of alanine will not. I got the question, why do them being part of peptide bond letting them not important? What that means is that if they are in a peptide bond, they cannot be ionized. They cannot gain or lose a proton. Here's our model of our peptide bond. This right here would otherwise be like this. Would be a carboxylic acid, would be a carboxyl group that can lose or gain a proton. But whenever it's in a peptide bond, this is gone. I hope that helped. Now, if we go on to the next one, arginine. When arginine is in a solution with a pH of 1, will that R group be protonated? Essentially, is the pH lower than, yeah, it will. So we're going to have a positive charge for arginine. Arginine is a polar positive residue. I can tell you right now, it's 12:48. I'm going to finish this example out. If you have to leave, though, go ahead and leave. And if you've got questions, email me. I'm glad to meet with you tomorrow during makeshift office hours or something else. I'm going to finish this out, though. But I don't want anyone to be like, oh man, I hope he finishes. Okay, next up is lysine. I omitted the N-termini of lysine because it's in a peptide bond. I don't need it. The R group of lysine. Lysine is a polar positive residue. When the pH is 1, that group is going to be protonated and it's going to have a positive charge. Last but not least is the C termini of lysine. When my pH is below, there was no poll today. There are no poll questions. Lysine, the C termini of lysine, well, it's protonated when my pH is 1, and it's going to have a charge of 0 because a carboxyl group has a charge of 0 when it's protonated and a -1 when it's deprotonated. Absolutely. Thank you. You too. Now tell me, anyone in the chat, what is the overall charge of this molecule at a pH of 1? +3. Perfect. I'm going to make my number line. When I deprotonate one group, what's the charge going to be? Then I'm going to go on to +1. I'm going to go to 0. Let me make sure that I've got check, check, check. 4 groups that are ionizable. I've got 4 pKa's. So how many arrows should I have? 4. So ARK is a tripeptide that can have a charge as positive as +3 or as negative as -1. At different pHs, it could be +3, +2, +1, 0, or -1. Could this peptide ever be -1? Absolutely. Could it ever be -2? Nope. Could it ever be +5? Nope. Now, M. I like that. Mo way. Now what I'm going to do is I'm going to write out my pKa values from lowest to highest. Left-hand side, 2.18. Then 9.87. Oh man, and I'm going to take a pause here. I started with my C termini, then went to my N termini. Does the sequence matter? No. Nobody cares. That sounds cold, but we don't care. We are going from the smallest number to the largest number. So 2.18 to 9.87 to 10.53 to 12.48. Can you give me a Z in the chat if you follow or an R in the chat if that doesn't make any sense? Okay. Now can you tell me, hey, what is the PI of this molecule? The pi of this molecule is calculated by adding 10.53 plus 12.48 divided by 2, and you get 11.49. 100% of my molecule has a charge of 0 whenever my pH is above 10.53 and it's below 12.48. And that happens to be 11.49. Okay. I've got some examples of how to do this calculation or these calculations that I'm going to put up on our Canvas page. I got a couple of old ones from my YouTube channel, and it's just about tripeptides or calculating pi of a dipeptide, I think. I'll add those. Other than that, though, thank you guys very much. I hope that you found value in this last few minutes. Um, this really looks at a lot of different things. There is no homework due tonight. If that's the due date on the Canvas page, that needs to be corrected, and I will correct that. I will post your homework a little bit later today. Like I said, I have it on another computer. I have the file on another computer. I got to copy and paste that. Um, I hope that you got value from this. If you have any questions, please don't hesitate to contact me. I'm glad to set up a time to meet with you and go through more examples of this, individual amino acids. Let's get to the bottom of like what you understand and what you don't understand on this. Other than that, though, I hope you guys have a great weekend. Thanks for coming and thanks for participating in class, and I will see you guys on Tuesday. Thanks, everyone.